Hi, welcome to the last video on asymptotic notation. So in this last part, we are going to review the theta notation, and this notation was introduced specifically for the computer science area by Donald Knott in the 70s. So let's go first to the image. You can see here, this is the function we want to analyze, and as with the previous images, we have here the input data size. In our case, is the input data size that is relevant for our running time or memory space, and the vertical axis is running time or memory space. And this is the function we want to analyze, that it might be running time like here or memory space. And we are searching for one function that has this condition. If I multiply this function for one coefficient, this function is always going to be equal to or higher than my function starting at some point. And if I multiply this very same function by another coefficient, I always get this new function going under my function starting at a given point called n0. So if I find a function that complies with this, then I can say that my function, the function I'm analyzing, the running time, for example, is theta of gn. So formally, this is a function I'm analyzing is theta gn if there's exist positive constants c1, c2, and n0 such that my function, the function I'm analyzing, is always between these two multiplied by different coefficients for all n higher than this. So if we go to our example, and this is the function describing our running time, you can see that n to the square, that the blue line here, it's always under our black line. So we have found a function multiplied by 1, which is always under our function. If we multiply the same function by another coefficient, for example 25, we will see that starting at 2, this function is always higher than our function. So we have found a function that complies with this. If we multiply the function n to the square by 1, it's always lower than our function. And if we multiply n to the square by 25, it's always higher than our function starting at 2. So this is the condition. Here, there's a mistake here. This is not 5, this is 1. So we have found a function n to the square that complies with this condition for all n's higher than or equal to 2. So we can say that Tn is theta of n squared. The theta notation, unlike the big O and the omega notation, refers to only one function for which there are constants such that this condition applies. So this is a really tight bound, and it's really useful because if your algorithm can be described in terms of theta, you have a really tight bound. Unlike big O or omega that refers to a set of functions, big O refers to a set of functions that are over our function, and omega refers to a set of functions that are under our function. Theta is much more precise because it refers to a function that somehow sandwiches our function. So that's the end of asymptotic analysis, and that's the end of our videos for this topic.